We've now talked about the Schrödinger equation and the fact that out of that equation we get these wave functions known as psi, and wave functions are also called orbitals. And so now we get from this equation, we get a description of where the electron is in terms of some quantum numbers. The wave functions have different quantum numbers, which are basically labels for the different wave functions, the different locations that the electrons can be in. Okay, so now we're going to go through the different quantum numbers that describe these wave functions. So these are quantum numbers. And they are quantum numbers because it's a result of the quantization of energy in packets. All right, the first label, the first quantum number is n, and n is used to describe the shell, what's called the shell of where the electron is, and that gives you the size of the orbital. And size is the same thing basically as how far from the nucleus, so distance from the nucleus. So how big the area that the electron is in takes up. All right, so this is known as the principal quantum number. N is the principal quantum number. And it is basically a counting number, 1, 2, 3, etc., etc. So it is made up of the counting numbers. Now we'll explain more about this in a bit, but first we're going to go through what the other quantum numbers are. All right, the next quantum number is called L, small case l, and that is known as the subshell label. And that gives you the shape of the orbital. So where is the electron? What's its shape? N gave you how big it is, L gives you its shape. And this is also known as the angular momentum quantum number. And it is going to be an integer, just like n was, but not a counting number, because counting numbers start at 1. This is actually a whole number, more specifically a whole number, because they start at 0. Okay, so it goes from 0 to n minus 1. So whatever value of n you have, it can go up to that number minus 1. So, for instance, if you are in an n wave function that is 1, then L can be 0, because n minus 1 is 0. So it goes from 0 to n minus 1. If n is 2, then it can be 0 or 1. And if n is 3, it can be 0, 1, or 2. So it goes from 0 to whatever n minus 1 is. All right. And the third label we're going to talk about for now is M sub L. That tells you the orientation in space of that wave function. Where is it directed? Which way does it point? And this is also known as the magnetic quantum number. And it is an integer, but not a whole number. And it goes from negative L to L. So it can be negative. All right, so let's say L in some case is 0. Then M sub L will be just 0, because from negative 0 to positive 0 is just 0. All right, if L is 1, then it could be negative L, 0, and 1, going by integers. If L is 2, it can be negative 2, negative 1, 0, 1, 2, and hopefully you get the idea. All right, so those are labels. Now let's see what we do with them, or how they make sense. All right, let's go down to the bottom here. Okay, so now let's put together all these quantum numbers. So remember that n is the principal quantum number. L is the angular momentum. Quantum number, and L is the M sub L is the magnetic All right, and then we said whenever, so the n is the counting numbers, and we have the first energy level is n equals 1, and then 2, and above we'll have 3. And remember that it also, n gives you the distance from the nucleus. All right, so whenever n equals 1, we said that L can be 0 up to n minus 1. So in this case, it's just 0. L will be 0. And so and then we'll go back to m sub L in a few minutes. Right now we will skip up to n equals 2. When n equals 2, L can be from 0 to n minus 1, so that's 0 or 1. So it splits into 2, 0 or 1 in L. And finally we'll go up to n equals 3, and of course you can keep going, and I'll have you practice one in a minute. It goes from, L goes from 0 to n minus 1, so it goes from 0 to 2. So this is going to split into 3 levels, labeled by 0, 1, and 2 in their value of L. All right, let's go back down to the bottom. Now, what can m sub L do? M sub L goes from negative L to positive L. Okay, for 0, it's trivial. Negative 0 to positive 0 is just 0. There's no choice. Now, this one, this level, we go up to n equals 2, but we also have an L equals 0. It's going to be exactly the same as L equals 0 down here. From negative 0 to positive 0 is just 0. But let's do a more interesting one. When we get to 1, L equals 1, m sub L can be negative 1 to positive 1. And we will draw the 3 levels and label them underneath as negative 1, 0, and positive 1. Okay, so now let's go up to n equals 2. And again, L equals 0 has only 1 m sub L. L equals 1 has 3, just like it did below, because the values of m sub L depend only on L, not on n anymore. Now, it gets more interesting. L equals 2 goes from negative 2 to positive 2, so there's going to be 5 levels. Negative 2, negative 1, 0, 1, and 2. And just to remind you down here, angular momentum quantum number gave you the shape of the orbital, and magnetic gives you the orientation. And this will all make sense in a little bit. All right, let's have you try one. We only did it up to n equals 3. Now you draw the same type of chart for n equals 4 and label with the quantum numbers, and then count up the total number of m sub L levels for n equals 4. So pause the tape, go ahead and proceed. Okay, and I will do it for you. If n equals 4, okay, that's your value of n, then the possible L values are going to be from 0 to 3. Okay, 0 to n minus 1. So we're going to divide it into 4 different levels. And there's a reason why I'm splitting these up and down, whereas the m sub L levels I don't split going up and down, I split them sideways. And that has to do with energy. The way I'm drawing this, the upper levels are going to be higher in energy, whereas the different m sub L levels are all the same energy. All right, so let's label them. 0, 1, 2, 3. That's your label for L. And then we'll do the m sub L's over here. And just like we did before, m sub L goes from negative 0 to positive 0, it's just 0. So anytime you have an L of 0, it's going to look the same. Anytime you have an L of 1, it's going to divide into 3. Negative 1, 0, positive 1. L equals 2 divides into 5. Negative 2, negative 1, 0, 1, and 2. And 3 divides into 1, 2, 3, 4, 5, 6, 7. Negative 3. Negative 2, negative 1, 0, 1, 2, 3. And the final question, how many total m sub l's are there for n equals 4? If you count all of these up, total m sub l's, you find that there are 16. Okay, there's 16 m sub l levels, which is equal to 4 squared, and since n equals 4, this will always be true.